this diagram here, this nuclear coordinate in
So, good morning everyone. Welcome to the session on organometallic complexes and strong electron relations. I'm going to be quite strict on times this morning because I stopped them. And so first speaking,
Okay, so I want to tell you about some work that we've been doing for the last several years on strong electron correlation effects in transition metal complexes, with a goal towards primarily going after absorption spectra of metalloproteins. We stumbled upon possibly a small application in molecular transistors on the way. And so here's an outline, sort of in a very quick fashion, 40 years of experience solving problems with strong local correlations in quantum impurity models. And then the question, why not do these things that have been done for solids at the molecular level? Describe this physically motivated basis set reduction, a mapping to the so-called Anderson impurity model. Describe a little bit of work we've done on X-ray absorption near-edge spectra, and also tell you a bit about how the phenomena of correlated hybridization might manifest itself in transport properties of molecular transistors. Okay, so is there a laser pointer? Yeah. So, well, we're getting a laser pointer. I think it's a little extra there. Let's see. Where do I do this right here? No, return. So red to the red button. Oh, it is. Okay, so the basic idea is that you have a transition metal ion or rare earth or actinide ion embedded in a solid. It could be a metal, it could be a metal oxide. There's a very strong Coulomb penalty for multiply occupying the levels on that transition metal site. And then there's hybridization to the outer world of the ligands or the surrounding atoms in the metal environment. And what is known is that one will wind up with a antiferromagnetic coupling between the spins in the orbitals that are sort of weakly correlated or uncorrelated with the spins on the local moment site, on the transition metal or actinide site. And that super exchange or condo coupling in a perturbative formulation has this form, where epsilon D is the single occupancy level and epsilon D plus U is when you have some double occupancy. So this is an important point that is sort of the folklore of much of solid-state physics. And there are two pieces of local moment physics which an impurity model captures. One is the condo effect, where you truly only have a dilute concentration of these metal ions embedded in a solid. And there's famous resistivity curves going back to the 1930s, where one finds an upturn in the resistance of gold, for example, at very low temperatures. And then what Kondo showed in 1964 was that you could understand this upturn because there's a hint of many-body resonance formation. That is, at high temperatures, you have a weak antiferromagnetic coupling between the spin of the local moment on the open shell ion and the spin of the conduction electrons, which sort of run by at the Fermi velocity. And then at low temperature, they form a many-body singlet ground state of large spatial correlation, in which you just screen out the local moment. So you start at high temperature for the local moment, you screen it out, and the scattering off of this resonance state gives rise to the upturn in the resistivity. This is a non-perturbative process. One can't get this from anything like density functional theory, from any Hartree-Fock theory. One can't get this from certainly from, say, the B3LYP, the correlated, the hybrid density functional schemes. It is a non-perturbative phenomena associated with local moments interacting with other electrons. And then this is a piece which it might be that things like B3LYP can get right. This is the physics of the Mott transition, which also is reflective of local moments. So the idea here is that how do you get a metal insulator transition associated with strong electron-electron interaction effects? Well, if the Hugel or tight binding matrix element is very strong, then you can easily transfer electrons from site to site, occasionally paying a penalty with the Coulomb repulsion. But if the Coulomb repulsion becomes very large, you effectively will get a traffic jam. It costs way too much energy to multiply occupy a given site, and so you'll basically block the transfer of electrons from site to site. So for T much greater than U, you have weak correlations, and you might get antiferromagnetic order at half filling of a sort of itinerant variety, meaning if you have one electron per site, half filling, you can get an itinerant antiferromagnetism. But if T is smaller than U, then you'll get strong correlations. You wind up with a so-called non-insulator at half filling, and you have local moments with antiferromagnetic Heisenberg coupling. So coming from the insulating side, one has the physics of local moments, and then coming from the metallic side, one has the physics of extended correlations of the magnetic character between the electrons. Now, I should say that there's often brought up this example that if you look at the copper oxide parent compound of the copper oxide superconductors, you can describe that by a Hubbard model, more properly by a so-called related charge transfer insulator model. Density functional theory by itself, I think this battery is, density functional theory by itself predicts this to be a metal at half filling, whereas in fact it is an insulator with a 1.5 volt gap. So density functional theory in its standard formulations will not get the physics of the lanthanum cuprate right. And you can't add to density functional theory anything like Muller-Plesset or simple Hartree-Fock to get this right. But I should note that the B3LYP does get it right in the sense that it gets about a 2 eV gap for lanthanum cuprate. That's according to the Goddard group. And according to the Vienna group, it gets about a 4 eV gap for manganese oxide. The Vienna group has their own version of a hybrid density functional, which also does a very good job on the gap and does a better overall job on the properties than the B3LYP. So I have to tell you, this is one place of strong disconnect between the physics and chemistry communities. You will find papers in physics journals about B3LYP. Most of them are written by chemists, a few by physicists. You will find most of the people focusing on this strong correlation problem in the physics community tend to ignore B3LYP. And so whether that's justified or not, it's a fact, and there seems to be a cultural divide there. One thing that has been done in the physics community is to use the quantum impurity idea to go beyond, okay, I think sorry, that's okay. To use the quantum impurity idea to go beyond the single site or single impurity model, and this is using the so-called dynamical mean field theory. I can't do this justice in this brief time, but I want to give you a flavor of how it works. The idea is that if you have a lattice, a periodic lattice of correlated atoms, then you can pick one atom and effectively treat that as an impurity with a kind of self-consistency applied so that you make sure that in effect every single site is equivalent. With this dynamical mean field theory, effectively what happens is this site becomes an Anderson impurity model in a self-consistently determined medium, a self-consistently determined metal. So you have these strong local interaction effects built in, and it turns out that both the physics, the Kondo physics and the Mach-Hubbard physics emerge consistently in this picture. You can solve the effective impurity model with a given level of self-consistency via the 40 years of techniques that have been developed for the Anderson, thank you, and for the Anderson and Kondo impurity models. And so, for example, just to give you an idea of how this works, this is work that was done actually by Prushka, Cox, and Gerald some years back, but the point is it actually captures this physics quite nicely. And this is now the so-called Hubbard model where we have a simple lattice in which electrons can hop with a single Huckel matrix element from site to site, and they have a Coulomb interaction U whenever they sit on the same site. The U here is being measured in units of the hopping. So this is weak correlations over here, this is strong correlations here. This is the density of states that you plot vertically versus the energy here. The Fermi energy sits at 0. So at very strong correlations, one sees clearly the Mach-Hubbard insulating feature where there's no density of states at the Fermi energy. But at low correlations, one sees a coherent so-called Fermi liquid or quasi-particle peak. And this is the self-consistent manifestation of the Kondo effect in this Hubbard model. That is to say that because of the self-consistent Anderson impurity model, one winds up with a kind of self-consistent mini-body screening of the electrons by themselves that gives rise to this strong resonant structure in the vicinity of the Fermi energy. So the dynamical mean field theory in conjunction with electronic structure calculations has been used to capture the physics of a lot of materials. For example, one of the most spectacular applications has been to get the phase diagram of plutonium, the transition between the alpha-delta phase of plutonium correct. That was done by Gabi Kotliar, Sergei Savrasov, and L.Q. Abrahams. And also, Kotliar, Savrasov, and some younger collaborators were able to get the phonon spectrum of plutonium correct by using this method in conjunction with so-called frozen phonon calculations. Okay, This shows you how they got the double well alpha delta structure right for plutonium, and they can also get a resonant structure that is these states that resembles what's seen in photo emission. Now, so what about molecules? Well, that's odd. That molecule disappeared there. Okay. One thing we know is that there are now a couple of different organometallic complexes based on rare earths, so-called sericine and terbicine complexes, where one can actually see a molecular version of the Kondo effect. That is, you get a singlet ground state in which one has to use a full configuration interaction calculation to understand this singlet ground state, but one does see a singlet ground state which one can understand as a molecular version of the Kondo effect. Oh, there it is. There's sericine. I don't know why I had that come in with an animation, but there it is. Okay. Let's see. So our goal is basically to say, well, look, we've had the success of applying an Anderson impurity model for the solid state. We've had 2 examples, at least, of where it must apply in molecular context. The question is, can we apply it to correlated molecules in biology, chemistry, or also rare earth and actinide? And the strategy is to divide the problem into atoms of strongly correlated electrons, which would be like the transition metal or rare earth or actinide ions, with weakly correlated and more extended ligand states, which would correspond, for example, to the p orbitals of the oxygen, carbon, or nitrogen, or sulfur, say, in some of these contexts. We will apply the solution methods proven successful for the corresponding cases in the solids, and the upshot is that we will then apply the so-called Gunderson, Schönhammer, Zanen, and Zavatsky variational wave function method, which is an intrinsic CI method. The upshot is it will produce a physical basis set reduction. It won't be good for chemical accuracy necessarily, but it could be used for easily computing spectra, X-ray absorption spectra, Born-Oppenheimer surfaces, and electron transfer reactions, etc. And so again, the picture is that we have a local, this is energy going vertically and density of states going horizontally. We have a localized state from the transition metal or rare earth with strong Coulomb interactions. We have a hybridization B with extended weakly correlated ligands coming from the surrounding atoms. And so the first stage is to separate the weak and strong correlations out, and one can easily do some linear transformations on, for example, the density functional theory Hamiltonian to derive what you would call your ligand states and your transition metal states, and then you can read off the relevant hybridization matrix elements in between. This is just a proof of principle. This is reading off the hybridization broadening functions, we call them, but basically the hybridization matrix element intensities as a function of energy for one of the iron-sulfur complexes that is relevant, for example, in a number of biological proteins. We have a paper describing this published last year in Physical Review Letters. And then we can estimate the correlation parameters from the transformed Hamiltonian. We're trying to basically say, let's use a Hartree-Fock model of the Anderson Hamiltonian, and let's match the Hartree-Fock solution of the Anderson Hamiltonian to the density functional theory energy levels to extract estimates, for example, for U. The exchange integrals in multiple interactions in the Koster-Slater or the Slater integrals, we can derive basically from atomic physics. But the U is the one that involves screening that's a little bit tricky. And so, let's see. For example, in the case of this cobalt valence tautomer, we can get reasonable J values and U values from this fitting procedure and get a reasonable value for the bare so-called D-level position from fitting the density functional levels. So now, what's our approach to X-ray absorption spectra? Okay, so and why would we care about this? Well, so metallo-organic complexes, of course, are building blocks for new materials, but also, as we know from this workshop, but they're also building blocks in biology. Something like 1/3 of all proteins have transition metals at the active sites. We can't, as we've heard a little bit about here, you can't always get at these sites with crystallography or NMR. They aren't always soluble and they don't always crystallize. So X-ray absorption can provide a site-specific probe which is sensitive to the local coordination environment. And it could also be useful to get snapshots of sites in different oxidation or catalytic modes, either by a time resolve synchrotron studies or by flash quenching of the relevant structures. So there's a motivation, at least, for trying to develop something here. And why bother from the theory side? Well, there are 2 sort of existing theoretical codes available for experimentalists, both of which are strong in their own way and deficient in their own way. The Theft code by John Rare and Bob Albers is a relativistic real space approach for getting spectra. It's terrific for XAPs, But while it includes some correlation effects to the so-called GW approximation, it does not appear to include, it certainly doesn't include Hubbard physics. Now, the TT multiplets code maintained by the group, and they grew out of the Savatsky-Zanen efforts in the 80s, that is an Anderson model-based code which does a very good treatment of the local correlations and provides a simple approach to the complex physics, and it computes X-ray spectra. But the ligand orbitals are lumped together into generic reservoir states of given symmetry. So it's not very specific to the particular environment around a transition metal atom. So there is at least a theoretical niche sort of in between these two. Now, it might be interesting for FEF to be developed with B3LYP or some hybrid scheme. It isn't at the moment. So I'm not sure how well it would do if one tried that, but it's an interesting question. So again, our procedure is to apply Gunderson-Schoenhammer plus Lanczos to obtain ground state and absorption spectra. And we delineate the configuration interaction using states coupled by hybridization in the atomic limit. We also can include spin-orbit coupling, which will mix these states up somewhat. We thus have a physically motivated basis set reduction. So in contrast to the usual thing where you reference it to, say, the Hartree-Fock state in configuration interaction, we're referencing this to the atomic limit of the relevant transition metal or rare earth site. So this is a scheme like CI with singles, doubles, but it's around the atomic limit and not the Hartree-Fock reference state. And you can't disentangle these states by a simple unitary transformation. You can't transform to a molecular basis and disentangle these states. They are intrinsically configuration interaction. Now, this is a slightly old figure, but let me just explain it. It's a little hard to see, but this is a fit to the so-called cobalt valence tautomer molecules, in which you have a cobalt site that can change its valence and its spin as you go from low temperature to high temperature. The low temperature state is a low spin contracted state. The high temperature state is a high spin expanded state. The X-ray absorption spectra at the K edge look like this. At low temperatures, you have basically a single peak riding on top of a large absorption for the P edge, or sorry, for the L edge, going from the 1s, excuse me, not the L edge. You have a strong absorption going from the 1s to the 4p orbitals, and that's this overall background. And then you have a peak corresponding to quadrupole transitions of the 1s to the 3d levels of the cobalt. And you can explain this with spin orbit split lines around a single Slater determinant. Now, on the other hand, as you raise the temperature, you actually get a shoulder here plus additional intensity at this higher frequency. The additional intensity can't be explained in terms of the background K edge from the 1s to the 4p, but one can explain it by an admixture of states in which you have a quantum entangled admixture of high spin cobalt D7 with screened high spin cobalt D6, and that's what these states are over here. So one has spectral features coming from primarily from the cobalt D7 appearing here, admixed in a non-trivial way with the cobalt D6 appearing over here. And that's something that can't be disentangled by a simple transformation. Okay, so I only have 2 minutes, I guess. But I'll just show you a flavor of some of the things we've done on molecular transistors. Going back to this idea of the hybridization, we can extract the hybridization using our transformation from the density functional Hamiltonian. And one of the surprises that we came to was that you find a strong spin dependence when you do spin polarized density functional theory. You can find that the majority spin minus minority spin matrix elements for hybridization can differ by as much as 2.5 electron volts, as in this case of the manganese surrounded by water. So we did a whole number of complexes here, and we compute basically the ratio of this difference between the hybridization matrix elements to the average hybridization matrix element itself, and we wind up with numbers of order 1 or larger, as in the case of this manganese. And so what's going on is that this is coming from so-called assisted hybridization, a matrix element of the Coulomb interaction, and one can understand it schematically by saying that you have a one-body hybridization, and then you have an occupancy-dependent hybridization introduced from the Coulomb interaction with a ratio A between the occupancy-dependent and the one-body, and this ratio A can be of order 1 or larger. In fact, we found it sometimes was as big as 5. Another way to do it is to say that if you look, for example, at the simplest Anderson model, where you have a single orbital to hop in and out of, If you hop into the orbital, you can have a hopping matrix element T1, which would correspond to B, the hybridization, one-body hybridization. And if you hop to the doubly occupied state from there, you have a matrix element T2, and the factor of A times B corresponds to T2 minus T1. So you have different hybridization matrix elements for hopping from the empty orbital end or from hopping into the doubly occupied orbital. That's reflecting the occupancy dependence here. And a few things. This has been brought up before. I'm going to finish in about 2 minutes. This is brought up before in the context of novel superconductivity by Jorge Hirsch, by Zawodowski and Pintz, but it turns out that the sign of this correlated hybridization is wrong here to do anything on behalf of superconductivity. It's been brought up before as a possible explanation of conductance anomaly in quantum dots, a plateau at 0.7 e squared over h, but this doesn't seem to work, at least in this molecular transistor context here. And it's been brought up to explain unusual gate voltage dependence of the Kondo scale in molecular transistors. This might work, but there are some problems. And so basically, there are these molecular transistor experiments where you have transition metal complexes linked to ligands, linked to leads, and some recent ones have been done, which are quite interesting. And one thing we found from the correlated hybridization is that the occupancy dependence can actually lead to a potential enhancement of the conductance, in which you could possibly get a resonant enhancement. This is that coefficient A reflecting the ratio of the correlated hybridization to the single particle hybridization. We do indeed find evidence in some parameter regimes. So this is the G up minus G down over G, the conductance to the molecular transistor. We do find enhancement in some parameter regimes, although it's fairly modest, a few %. But this would be the the red curve is the limit where you have no correlated hybridization. In the purple curve, you have correlated hybridization. And I also just want to show you that if you look at this unusual gate, this is basically the gate voltage of your molecular transistor. This is the Kondo scale in the molecular transistor. If you look at the gate voltage dependence, for example, seen by the Nadelson group at Rice, we can find curves which reproduce that, however, in detail. To try to explain those curves from a density functional calculation, giving input parameters, it doesn't quite hang together. But we can at least generate curves which resemble those seen by experiment from our simple calculations. I realize this last part went by very quickly, so I'll just stop. If you have questions, you might ask them about that.
Okay, so throwing the floor open for questions.
Can I ask a question about that transistor setup?
Sure. Yeah.
I mean, you showed that you had the molecules between two leads.
Right.
With a transistor, you often have a sort of an insulating event. So how does the transistor work in that case if it's just, effectively a single molecule between two
well, I have to admit that I'm not entirely. The claim is that they can still tune the. So of course, if you have a quantum dot, it's easy to tune the effective level position with the gate voltage. I guess it's less obvious to me in the case of these molecular transistors that they have a strong control over the level position via the gate voltage, and that might be one of the other possible explanations here. Just assuming that you can linearly tune the level position with the gate voltage is what's being assumed in this context from the experimental side.
Is the assumption also that you've got a single molecule because
yes,
yeah. Because in essence, it's very hard to, with a molecule as small as that, to actually really know whether or not you've got a single molecule reaching your
yes, that's definitely the assumption. Right. So this is one of the usual complaints about molecular transistors. How do you know for sure that you've got just individual molecules in there? But that is true. Right.
But I guess my question is, from your modeling,
yeah.
You said, well, we've got something which looks fairly similar.
Right.
But if you then said, well, actually, we've got several molecules and model the effect of those, would you then say, well, actually, I don't believe you have a single molecule because...
No, we can't at this point. We don't. And for one thing, the biggest problem here is that, just going back to this picture, I think the biggest problem is that we're using, in this calculation, we're using a single orbital model. Now, of course, transition metal ions have orbital structure. We're in a little better shape with these from the Nadelson group because they're copper, so it's D9, and so to the extent that you have enough distortion of the copper molecule, the EG orbital will be fairly well split, and a single orbital model might be pretty good. But in fact, that's even not completely obvious for the copper model. So until we build it up to where we really are realistically treating the orbital degrees of freedom of the transistor, I'm not going to push it that hard. The only point we wanted to make was the Nadelson paper had suggested that maybe this correlated hybridization could play a role in giving this unusual gate voltage dependence to the Kondo, because they actually had expected it sort of a different sign to it rather than sort of flat and decreasing. They expected it to increase. That basically comes about from a shifting of the position of particle hole symmetry in the model, which they correctly identified. But I'm saying in detail, the numbers don't quite work out. So.
Is your model is good to predict the optical spectrum of metalloprotein?
Well, that's what we're aiming towards. So what we're developing is a fully automated way to go from density functional to Anderson model to L3 absorption spectrum.
So it will be able to take care of the solid band and as well as the Q band for the metalloprotein? Like around 400 and 500 region?
Let's see.
Is it optical completely? Optical?
Well, not optical. I'm sorry. This would all be X-ray absorption.
Yeah, exactly.
So,
that's
right.
But not optical.
No, not optical. No. This won't be good enough.
Yeah.
A question out of left field. The chemists play around with scanning tunneling microscopes.
Right.
A solution where there's a potential on the solution. So it's then a 3-electrode problem. I guess the theory for all that's been done by people like Kurtzenoff and Ostrov. But there's a direct analogy, at least in principle, to what you're doing here. But has anyone ever exploited that analogy? Looked at the mathematics? Does it all map over in any form?
For the SUN solution?
Yeah.
Not that I know of, but I haven't looked at that. So I don't know. That's a good question.
So perhaps I could ask you a question as well.
Yeah.
On the first system you looked at,
Yes.
is there anything you had the high spin state at
And again, I'm afraid I accidentally deleted it here.
So here, that picture there, so you had the high spin state is at low temperatures, is that right?
No, the high spin state is at high temperature. Sorry. So what happens is at high temperatures, you have a high spin state with an expanded volume. What drives the transition is effectively entropy. Basically, you can reduce the entropy in, if you go coming up from low temperatures, you can gain higher entropy by going to the high spin state. At low temperatures, by transferring a charge out from the cobalt to the ligands, you can go to effectively the state where the ligand field splitting is so big that you don't get any easy exchange and coupling. So you get the spin crossover, and then you get the low spin state. So the low spin state is well described by essentially a single determinant, modulus of spin orbit splitting. The high spin state, we're claiming you need to have a configuration interaction. This part gives us the shoulder, and the configuration interaction admixed to a high spin 3d6 state gives us the extra spectral weight out here. So this is the high temperature spectrum. This is the low temperature spectrum.
You mentioned calculations on cobalt complexes in different states, but in solution. Would the calculations show up any differential stabilization of one of the states minus oxygen?
Oh, that's a good question.
Because, for example, with something like a trivalent complex, it is calculated in some cases that you can get something like up to 1 electron volt stabilization of the high spin state. Crudely speaking, the electron power is more extended at the radius of the
Right.
Directly smaller. It goes to the square of the charge, so it may be a small fraction of the total energy.
Right.
A small fraction on both.
Yeah, right. That's a good question. That has not been suggested in the context of these valence photographs, cobalt valence photographs.
I can give you a reference.
For valence photographs?
No, I can give you a reference.
Yeah, that'd be nice. That'd be nice.
Okay, so we better cut this question short there. Thanks, Daniel. So the next speaker is Hubbard. He's going to talk about organometallic complexes for light emitting diodes, just the same as his distribution.